All right, here we go. Probability is basically the likelihood or chance of something happening. So let's, you say probabilities are always expressed in fractions or big decimals or percentages. Like say I've got a 70% chance of something's going to happen, or 1 out of 3 chance something's going to happen. That's what you're looking at with probabilities. So let's kind of go through some definitions and preparation of this here. And now in a probability experiment, we have what's called a sample space, meaning that's the set of all possible outcomes of that experiment. For example, we'll be using the single 6-sided die, single die, and 6 sides, so the outcomes, the number of dots would be 1, 2, 3, 4, 5, 6. That would be the sample space. Now each element or each item in that sample space is an event. Each one's a simple event. Event E is defined to be any subset of S. That little symbol just means the empty set. So obviously, if we're looking at 1, 2, 3, 4, 5, 6, we wouldn't have an event of rolling a 7 unless we were trying to get 0 as the answer. But so a simple event contains only one element, and a compound event if it contains more than one element. This is from another book, but this book also uses the phrase joint event. Compound event and joint event are essentially the same thing. An example of a joint event, we'll see several of them, but just give you one right off the top of that there. Let's see. If you roll the single 6-sided die and you're defining the event as rolling an even number. Out of the numbers 1, 2, 3, 4, 5, and 6, you have more than one of those that's an even number, 2, 4, and 6. So that's why it's called a compound. My instinct, I'm going to say compound event more than I am joint, because that's a term I don't, I haven't run across as much in my career as I have compound. Most books use compound, but that's all right. No harm. So sample space is, we're not going to be listing out gigantic sample spaces. You don't have to worry about that too much. But anyway, if you flip a coin, heads or tails, you got brackets wrapped around them. That's how we indicate a set of item. Here's the single 6-sided die, 1, 2, 3, 4, 5, 6. 2 children, boy, girl patterns. Got 4 of them. You can go girl, 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 boy, boy, girl, boy, boy, if you factoring the order in there. And here's one, that's the sample space. Now here's a couple of events. So let A be the event of 2 girls. Okay, well, there's only obviously one outcome there that represents 2 girls, the GG. But suppose this one says let E be the event of 1 boy and 1 girl. And so we're not specifying, it doesn't say in that case 1 boy, then 1 girl. It just says boy-girl combination. So that would obviously, if you're just containing 1 boy, it could be boy-girl or girl-boy. Isn't that exciting so far? All right. I can just feel the excitement in the air. I'm gonna get the My Math Lab opened up here, stop for a second and get that going. Well, I'm probably jumping ahead. I can wait on that, I guess, because we are gonna look at some homework problems, of course. And let's see, I'll just go ahead and sign in right now. Let me go back to this then. Back to the notes. Let's see. And now here's another one. E is kind of just you really use any letter you want. It doesn't really matter that much, but I'm just kind of using S is pretty much reserved for sample space, but to define an event, it's, not alphabet restricted here, except not S. Like here's one, we have a number wheel with numbers 1 through 18, and we have one outcome, a number divisible by 12. Okay, out of those first 18 numbers, the only number divisible by 12 is 12 itself. So the way that was worded, it looked like it could have been a potentially a compound event or joint event, but it wasn't. There's only one. Now how about the next one? It says an even number out of those numbers that is greater than 15. So how about the elements 16 and 18 being greater than, even numbers greater than 15? Does that seem okay? All right. the complement of an event. Complement, spelled a little different than the word complement where there's an I between the L and the M. Complement such as, oh, that's a lovely car you have, or something like that, or whatever. It's a beautiful whatever. Not that kind of compliment. It's an E in there. Essentially, it's denoted by this A with a little single, A prime is often the way to say it, but it means it's the elements that are in the sample space that are not in that particular event E. It's basically the same as the opposite of, not in there. So here's an example of the complement of toss at least one head. It's wait, at least is the subset. The opposite of it. Oh yeah, I'm sorry. Yeah, tossing at least one head would be H, H, T, T, H. Actually, it's the same as the boy-girl one, really, here for 2 coins. H, 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 T, same thing. So at least one toss would be to these 3. So the complement of that would be the only one that fits in there that's not the one of those 3, which is tail, tail. So it means it's not in it. So like, for example, another example. Too many numbers here. I'll go back to this. So let's say if we define the event A of this single die as what I say earlier of not of an even number, being an even number. That was 2, 4, and 6. So the complement of that would be everything else in the sample space that's not 2, 4, or 6. So it'd be 1, 3, 5. So complement means just that the things that are in your sample space that are not in whatever the particular event is that you're defining. So that's not too bad. All right, probability. Now, obviously, you can determine how many elements you have in a certain event and how many elements you have in a sample space. But that's not what probability is. Probability is always something that's divided, meaning it's always the number of elements in your event divided by the number of items in your sample space. So, we're going to look at lots of examples of this. I keep referring back to these other ones. So, but I'll pick this one right here, the B on the other page. So that means that there were 2 elements in this sample space of even numbers greater than 15. So then now I'll write this here. I'm not going to leave it in the notes. I'm just going to write it right here so you can see it. Probability of E would be 2 out of 18, which, mathematically that's correct. I guess we should be polite and I guess reduce the fraction, but there's nothing mathematically wrong with the answer 2 out of 18. Now, how about if I say this? Now, there's 2 ways you can do this. You could, the more cumbersome and least desirable way is you can count through and figure out that there's 16 numbers out of those 18 that aren't in that E. But another way you can do this now this only works for probabilities, not for how many items there are. But if you're talking probabilities, the complement is always 1 minus the probability of the event itself. So you could go 1 minus 1 out of 9, and that would be 8 out of 9. So you got an 8 out of 9 chance that you do not do that. Now, if you look at these 2 numbers, that's kind of ties in with that formula. You can see what these 2 numbers add up to, and that's what it would always add up to. Any event, the probability of any event plus the probability of its complement is always equal to 1. In fact, that's where this formula comes from. If P of E plus P of E prime equals 1, and you just move 1 over to the other side, you have subtraction then or whatever. So, all right, complements. I'll erase that now so I can move back down, see what's going on here. I'm not going to just read through this entire thing here. There's just, you can look at this later. But let me just, I wanted to put this information there. I want you to see it. But the main thing I kind of want to hit on this is, when you're calculating any probability, if you're talking decimal, fraction, that kind of notation, your answer always has to be between 0 and 1. Always. Now, if this is in percentage, that's the same thing as saying 0% to 100%. So then if it's percentages, then it's, whole number percentages. So a probability can certainly be 65%, but as soon as you convert that to decimal, that's 0.65, which is between 0 and 1. So if you're working some probability problem and you swear the answer is 1.2 or something, I'm doing this all, I get 1.2 every time, you're doing it wrong, because it cannot be 1.2. It cannot be negative. It can be those extremes, meaning you can have a 0 chance of something happening. That's certainly possible, but you cannot have you can have 100% chance of something happening. Like the examples of those would be, let's say 0 would be, suppose rolling a single die with 6 numbers. What's the probability that I roll a 7 die? 0, because there are no outcomes that have 7 dots on it. But then what if it was phrased, suppose that I roll the number of dots facing up is less than 7. Well, every outcome on there is less than 7, so you would have a 6 out of 6, 1, or 100% chance that you would roll a less than 1. So that's a lot. Yeah, so you can have an impossible event. Another terms for that is 0 is called an impossible event, and 1 would be a certain event. You don't need those terms for testing purposes or anything, but meaning absolutely guaranteed. Let's see, and we'll talk more about this one actually later. All the probabilities have to add up to 1. That's going to come up in this same second unit of the course, but we'll see that a little bit later. It might come up a little bit here. Well, this is a commonly studied thing in probability. Use reference deck of playing cards. All right, you don't have to become a card game expert in this class. I haven't, when I've taught that finite, I haven't taught that finite math in a while, but when I used to teach that and we did this, and people freaked out if they're not familiar with it. You don't have to learn any particular card games, but you just learn this diagram, which you can obviously refer to whenever you need. You don't have to memorize it, just how to interpret it. This is what your standard 52 card deck of playing cards looks like. We have what's called 4 suits. Those are called suits. Hearts, clubs, diamonds, and spades by their symbols. And you see that half of them are red and half of them are black. And we have what's the A is called an ace. And then these 3 picture cards, or I'm still used to calling them face cards, but it's either way, it's the same thing, a picture card or a face card. That means the card's got somebody's face on it. Kind of makes sense, right? None of the other ones have a face on it. And we're going to look at, can we calculate probabilities coming from picking a card out at, random from that deck. It's good. It's good for building probability skills. Here's what I'm mentioning earlier about probabilities must be between 0 and 1. So we'll come back to that card thing here in a minute, but there are 3 basic types of probabilities, known as theoretical, empirical, and subjective. Theoretical is based on strictly the number of events in a sample space. And then empirical is based on measured outcomes. Let's see. And then subjective is based on just a personal feeling. But anyway, let's kind of go through each one of these. And I'll use other examples in addition to this one. But flipping a coin, 2 outcomes, heads or tails. So your sample space has 2 elements. So in theory, anytime you're about to flip a coin, you've got the theoretical probability is whether it's heads or tails, because only one outcome of each. You've got a 1 out of 2 chance of flipping a head or flipping a tail. Now, empirical probability is based on actual measured outcomes. Empirical probability is very similar to what we've learned with relative frequency. It's similar to that idea. So let's say we come down here and we flip a coin 50 times and we observe 28 heads and 22 tails. Okay, so we would then, we would say that in this case, the probability of heads is 28 over 50, probability of tails is 22 over 50. Even though that doesn't really necessarily influence anything, that's just what it is. Empirical probability is essentially relative probability. Now I'm going to leave this here a second. I should have I just realized something I would like to paste in the notes. I mean, it's not necessarily something to be tested on. I may go back and add this little blurb I'm about to show you in the notes and then repost them later, but I'll talk about the subjective here in a second. But there's something that relating the theoretical and the empirical that I want to show you. I know the screen's not up yet, but I'll switch over in a second when I have what I want selected here. Because what I did in the Stat 3309, I kind of went through a basic summary of this stuff. So I'm going to switch screens and I'm going to cut. I'm not going to do it right now. I'll cut and paste, or I'll do it later and then repost the notes. But I'll switch screens just so you can see what I'm about to talk about here. So this is, you won't see this if you're actually looking at your notes, but I'll add it in there. I may add it in at the end so I don't have to redo the entire thing here. So now you should be looking at something on your screen that says the law of large numbers. That's what, I mean, it's not a big deal if I don't go back and put it in the notes, but I think that I might, especially now that I'm about to talk about it. It's an idea of relating empirical probability to theoretical probability. I use that 50 coin toss. Now, assuming everything's on the up and up here, and I'll talk about that here in a second, if you actually perform an experiment and you're measuring the empirical probability over time, and there's no real exact definition of very large, I'd start with at least a minimum of a million to consider very large, but someone could argue, no, that's not large enough, 10 million. It's not a specific amount, but it needs to be a lot. You would expect the empirical probability to be very close to the theoretical probability. For example, suppose you flip a coin 10 times and you record the outcomes, the heads or tails. And suppose you get 9 heads and 1 tail. That's not really a big deal in only 10 tries. That's certainly within the reason of possibility that can happen. We wouldn't be that concerned about anything being wrong. However, now it's a human being flipping one coin 10 million times is probably not from a time standpoint, but you just have to humor me on that. But suppose the coin was flipped 10 million times and you got 9 million heads and 1 million tails. You know what that tells us? That tells us we probably got something wrong with our coin. That it's not fair. It could be weighted kind of funny or something, whatever the case may be. Same thing with, that's too many of them. In other words, 10 million times, it doesn't mean you're going to get exactly 5 million heads and exactly 5 million tails, but you are certainly expecting it to be somewhat close to that, somewhat very, very close to that. Or if not, something's wrong. Same thing with, saying like a single die, roll a 6-sided die. If you did this millions and millions of times, each one of those has a 1 out of 6 chance. But anyway, you would be expecting an equal number of outcomes. Let's say 6 million times, you'd be expecting about close to 1 million of each number. to have come up. If not, something's wrong. And dice are actually kind of funny because, you know, the interesting stuff that in past years, what people have tried to do to cheat in casinos. And one thing is that they filled the holes with lead and then covered it up white and try to sneak loaded dice into a game. Yeah, when they're loaded, it's because they're weighted funny like that. Maybe some lead to alter the roll or something like that. And that's what I was talking about. If you had I'm not sure how you would actually do that to a coin really, but to a die, single die, you could do that and sort of rig the outcomes or it's not evenly distributed. So, all right, so let me get back off of that. So that's how those two relate together. Let's go back to where we were in the notes. So I think I might add that little clip back in there, and that little bit in the notes, even though it's not really something I would test on, but I think it's an interesting top part of the topic of how these two relate to each other. Subjective is using a probability based on, like I think I mentioned up here, personal feeling or something like that. You know, I'll use a better example than I put here, but I think there's a 60% chance of flipping a tail on the next toss. Well, so it's anything that's not based on measurements. Let's say before you started this course, let's say, I feel like I got about an 80% chance I'm going to make an A in this class. You know, you're just kind of speculating based on personal feeling. But the key is, though, it's still got to be between 0 and 100 to you know, follow the laws of probability. You know, it can't be outside of those range. So I always laugh when I hear the expression that's when somebody says, you know, I gave it 110% effort. And I always think to myself, no, you didn't. That's impossible. You're only giving your maximum. I would believe someone if they said they gave their 100%, but you know, everybody uses that 110% to act like they're giving more than they possibly could. But it's pretty humorous. But now I put that in your brain now for you to think about. But yeah, no, you didn't. You could put in your max 100, but you didn't give 110%. That's impossible. Anyway, from probability standpoint, I'm not talking about other types of things where you can go over 100%, but just probability you cannot. Let's see. Let's look at contingency tables. We're going to be looking at this was defined in one of the other sections, contingency row column tables. I don't think we did much with them back then, but now we're going to have a little fun with them. Let's see. So, you know, oftentimes there'll be words here instead of, you know, symbols, but that's all right. Well, let's look at how these work. Let's see. So we have A, and these could actually have more than two things over the bottom. They can have more than two on the across, but what I labeled them as A. And if there's only two items, whatever is not A can be labeled as A prime. Remember the complement we talked about a little while ago? That would be the complement of A. And across the top, we have B and the complement of B, B prime. And then everything on the inside are ands. Ands means what's in common between the two. So where A meets B is where A and B are in common. I'll write something down here for a second and show you. And this one is not A and B. Then across over here we have A and not B. And then we have A prime and not B prime. Now the totals, so the total would be how many B's there were in the first column, how many B primes there were in the second column, how many A's there were in the first row, how many A primes the first row, and those are the totals, and this adds up to the grand total of however many items you had here. So I'm going to write, and then we're going to see these written as whole numbers, and then we can obviously all we have to do to convert them to probabilities is dividing by the entire. So let me just write, just to give you an example of the and idea there. So let's see, I'll use it with single die, rolling an even number. B, rolling a number divisible by 3. So let's figure out what's in A. 2, 4, 6. What's in B is 3 and 6, correct? Now, we know there's 6 total. Now, it's interesting. All you really need is just a few things here, and then you can complete the whole table without doing everything else. I can list out, show you what I'll just tell you what the primes are. But anyway, A and B, they do share they share one common thing, don't they? So there's one element of A and B. The total number of B's is 2. The total number of A's is 3. Now, really, that I can complete. I don't have to even list out the A primes and the B primes. I can complete the rest of that because everything has to add up row, across, and down. So I'll use a different color to put in the new numbers here. I'll use purple. So you actually have enough to finish this. So if this is the 2 and that's a 6, this has to be a 4. If that's a 3 and adds up to 6, that has to be a 3. And 1 plus something equals 3, that's going to be a 2. And then adding down, 1 plus something equals 2, it'd be a 1. And then 1 plus something equals 3. And then look, you can double check. Look at that. It worked out. 2 plus 2 gave me that 4. 1 plus 2 gave me that 3. And it all adds up beautifully there. Pretty exciting, isn't it? A lot of times we're just going to be dealing with numbers that are already given in there, you know, or that sort of thing. I don't think we're going to have to really go about it this particular way or whatever, but so a lot of times I'll be using larger numbers anyway, so there's no way we want to go through this one, but this was not a bad process just because it was only a handful of numbers to deal with. So, all right. But I mean, I'll just mention real quick. So that means the set A prime would have had everything that's not in A. So it would have been 1, 3, 5. B prime would be everything that's not in here. So it'd be 1, 2, 4, 5. Everything not in there. So, all right, let's come down here and look at Venn diagrams. Let's come down here. Let's see. So the good news, that'll be, you know, saved in the video. So even though I erased it. Venn diagrams sort of help visualize the sample space. Now, I'll fill out the Venn diagram, even though I just erased that. I should erase that one. And I'll actually write the elements in there instead of how many there were. Now, sometimes you'll see this symbol used, intersection. And means intersection, and it's also written down with that little upside down horseshoe. Is also those mean the same thing. Upside down horseshoe means it just means it's in both A and B. And the sticking up horseshoe looks sort of like a U, but it's more of a horseshoe, means it's in either A or B, which represents the entire region. So if I go back and show you, so that the middle part here is the intersection. So if I go, now so this time the numbers I'm writing in are the actual sample space numbers, not how many there were. Like earlier we saw where A intersected B and there was one item in there. Well, I'm going to write the number 6 just because that's the 6 that fits in there. And B was the one where it was divisible by 3, so there was a 3 and a 6. And this one had even number. So these are the numbers that are floating around in there. So you see the entire circle of A contains 2, 4, and 6. The entire circle of B contains 3 and 6. Now, the entire box represents everything that's in your sample space. So everything that's not in the circles has to be floating around in that box somewhere. It doesn't really matter where you put it. So there are 2 numbers that don't belong to either one of them, right? There's the 1 and the 5. So you can just kind of put those wherever, 1 and 5. But the box then contains all 6 numbers. And then the Venn diagram shows what belongs to what. So you see, that's why you know there was one item that was in common between the two. So the, I think we got that okay. So for example, then A prime means everything that's not in A. Remember that inner circle is part of A, so everything that's not in A is floating around outside the A circle. And then B prime is floating outside. See, the B circle has the 3 and the 6. So everything outside the B, including over here and outside there. So it'd be 1, 2, 4, 5. All right. So Venn diagrams. Very useful to help you visualize this stuff. Let's come down here and look at something called marginal probability. We'll see. We'll wait till actually this comes up. I didn't define collectively exhaustive events, and I'm not going to do it for any test. In fact, I got rid of the homework problems on that. It's too. We're just going to stick with mutually exclusive. That's good enough. Collectively exhaustive is not really useful nor necessary, but it's hard to really make much sense of this formula until we saw it in action. But it just means it's the probability of A. Well, actually, I can go back up to that little contingency table and show you that to make a little more sense out of this formula. But you really wouldn't need that formula with this table anyway. But so let's say if we were trying to find the probability of A, which is actually going to represent how many numbers are in this A divided by the total, that's going to be your probability. So if you already had that number, it's pointless, but it's just saying that to get to A, it's these two added together. It's A and B, and then A and B prime. Now suppose we had more than 2 things across the top. It would be everything that's on this row, all the ands added together, and that gets your total. So it's kind of a fancy way of taking something that's really not that difficult and making it more complicated looking, basically. So that'll actually come up in the next section in a little more detail. But right now, it's not that big of a deal. But I'll show you one when we get to an actual problem. I guess depends on, like my math lab might give us something where it only gives us that information, and we may have to use this. Then we'll just use that formula directly. In other words, maybe in my math lab problem, I wouldn't do it on a test, only gives you these 2 values and does not tell you how many total ones are in A, then I guess we would be forced to use that formula. Now this one's important. It's the general addition rule for how to find unions. And so the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. Now the minus is very important. The minus is there so we're effectively preventing what's called double counting. Now for this one you could do pretty easily if you wanted to do it without the formula, but obviously I want to show this formula because we're going to need this formula. But for the 6-sided die, meaning we're saying, you know, there are the 2 events, rolling a number divisible by 3, and then so that contains 3 and 6, and I'm letting B be a number less than 4. So it's just 1, 2, and 3. So notice they share a 3. So if you're trying to figure out how many, the probability of being either divisible by 3 or less than 4, you only want to count 1, 2, 3, and 6. You don't want to count 3 2 times. So the formula takes care of that because it removes one of them. So the probability of rolling a number divisible by 3, there's 2 here, events out of 6 total. It's 2 out of 6. This one, 1, 2, 3, makes 3 out of 6. And then you subtract the one that's in common, the A and B. There's only one of them, 3, 1 out of 6. So you get 4 out of 6, so you have a 2 out of 3 probability chance that you're going to get a number divisible by 3, or it's less than 4. It's got to satisfy both, and means it's got to satisfy both at the same time, or means it satisfies one or the other. I'm just going to jump ahead for a second. I'm looking to see if I mentioned, well, I'll go ahead and say it right now. If your events happen to be mutually exclusive, meaning there's nothing in common, that's okay. That just means this last part's going to be 0. You'll have nothing to subtract from it. So you might think, oh, I'm missing something. I don't have all the information. No, if they're mutually exclusive, that number will be 0. And just nothing. You'll just add the first two together, and that's it. Okay, card problem. So I'll scroll back up to the deck. We got 2 events, drawing a king, drawing a red card. Okay, everything's going to be out of 52, so that makes the denominator easy. Not counting if it's reduced or whatever, but I mean, out of 52, so we just have to figure out what's in the numerator. Where's the card picture? 52. King. Kings are right here. 4 kings. In fact, there's 4 of any one particular card. 1 for each suit. There's 4 cards. Each suit has 13. 13 hearts, 13 diamonds. Those are your red cards. Together, that makes 26 red cards. Now, before I scroll down, we have to ask ourselves, is it possible for a card to be king and red at the same time? I do believe that's possible. Let's see what we got. I think the king of hearts is a red card, and the king of diamonds is a red card. And king. Red and king. 2 of them. So that's, I wanted that way when I scroll back down there, I'll scroll back up again, at least right now. So so you see there was 4 out of 52 was a king, 26 out of 52 were red, and then we subtracted the 2 out of 52. So those 2 that we were subtracting are actually both a part of the first 2. They've been counted twice. We don't want double counting. We only want them to be counted once. So one of them was removed, and then we get 28 out of 52, and the rest of it's just the reducing process. I personally don't care if fractions are reduced, but of course, who knows what they're going to ask for. In math lab, they might ask for, decimal to a certain number of places. Okay, here's just bringing up mutually exclusive again, talking about the probability of being 0. Like suppose a question, it actually relates to the next question, really, but same thing. It's king and jack. There's no way a card can be both a king and a jack at the same time. So that probability would be 0. Same thing is going to happen right here. Probability of drawing a queen or an ace. I'm just using 2 new letters here, C and D, to define your events. And like I said earlier, any letter's fine as long as it's not S. C, union. I could have just put the word or there. Maybe I'll change that to or. But I showed you earlier they're the same thing, but that sort of matches with this book notation a little bit better. I'll write the or here. All right. 4 queens. 4 out of 52. Plus 4 aces. 4 out of 52. 0 here because there's no card that can be both a king and an ace at the same time. So there's nothing to subtract. We get 8 out of 52. Ta-da! And that reduces to 2 out of 13. Now here's the contingency table for us. All right. 1,000 people. Sometimes these contingency tables may not give you these totals here. They may not. But as long as you have the inner numbers, so watch for that when you're doing a homework problem or whatever the case may be. As long as you have these inner block of numbers, the totals are strictly just adding across the rows and adding down the columns. So that's not, oh no, I don't have the totals. What am I going to do? As long as you have all these inside numbers, you're good. No need to panic. So here's a couple of or questions on this. person is left-handed or a woman. So it's kind of following. You know what? Let me copy this down. That's what I'm going to do. So, these notes are going to get reposted anyway, obviously, with that law of large numbers and stuff. And, I mean, obviously, I don't see any major problems with it, but not enough that's hurting our lovely lecture here. All right. But I'll just resave it after I put all this back in there. Oh, that's not where I'll go back up a little bit. Just so I want you to be able to see that as we're looking at it. Shrink it down a bit. There we go. All right. Now this one, so we have left, right, and then men, women. I'm just laughing. I was thinking about, don't let this notation bother you here, especially the women. I don't want you to feel like that you're being labeled here as not man. But anyway, that's it. Because it looks like that, doesn't it? Men, not men. But no, you get your own identity here, women. So left, right, men, women. Left-handed or a woman. Actually, I would like to rewrite this out anyway, so I'm going to erase this. I'm going to write them as angled fractions so it looks a little better. And you can watch me do it here, so shrink this in a little bit. So L or W. Now you still use it. You can use A and B anytime you want. Like I said, that's not critical here, so I'm just using obviously L for left and W for women. So it's the probability of everything's over 1,000. So you're dividing by 1,000. You're always dividing this stuff by your grand total. Something we do in the next section is a little bit different, but this is your grand total. How many left-handers do we have? 113. So I'm going to go 113 divided by 1,000 plus women down that column, 475 divided by 1,000. Do we have people that are both left-handed and women? Absolutely. Those 50 represent and. Remember I told you earlier, anything inside the box is and. So minus that 50. I'll just leave this part. I won't. So long story short, then you end up with 538 divided by 1,000, which is 0.538. All right, that was fun. Let's do the next one. That will be the end of this section. Next one says right-handed or a man. All right, let's see what that's all about. Probability of right-handed. Go across here. I see 887 out of 1,000. Now, sometimes these contingency tables could already be given in probability form. So obviously, if you see them already in decimals, you don't have to divide. That means you would have a 1.00 here at the end. So if you could divide, but you'd just be dividing them by 1, which obviously doesn't change anything. Probability it was a man, 525. Is it possible to be right-handed and male? I believe it is. So I got to subtract that off. Minus 462. So I've done this problem before, and that should add up then to 950 over 1,000 if you add that up. And then, of course, making a decimal makes it 0.950. And there we go. I'll go ahead and save this for now. And like I said, add that law of large numbers back in there I talked about earlier. Can't decide if I want to add it back in where I talked about it, because then I got to move all the notes down. It depends if I don't know if I feel like it, whatever the case may be. That takes care of this section. Oh, homework. Sort of takes care of it. I promised you a homework. Let me. All right, well, I'll switch over whenever it gets ready. I am curious though while I'm doing this, and that's no big deal, but nobody has to. It'd be better if you put it in the chat, if you felt like putting this in the chat. I'm just curious, because first time I've gone through this in this class, because it wasn't done this way before. Or if some of you feel like, you know, yeah, you know, I remember all that from whatever they call the third. Well, it's 1305 is the course number. I'm just curious what your opinion is. You know, do you feel like that was a total review and you already knew it, or you knew some of it and didn't know some of it? I'm just strictly curious. No one has to reply, but it'd be better if you put it in the chat instead of just kind of yelling it at me. I'd rather you just, if you're going to use vocals, is for, you know, because you're stuck on something I'm explaining or whatever, you know. I'm just curious of how that went, you know. I mean, I'm doing this whether even if you all say, you know, oh, I won't ask this again after that, probably, and maybe after this section for sure, because I know what we're doing in 4.4. Well, I'm gonna say maybe some instructor covered it, but most of them probably didn't. So that probably will be new. But this one stuff you may have already seen, and then the next section. But the next one, though, even if you have seen this, I think you're gonna benefit from seeing this again for sure. Conditional probability. That's a little trickier. So let me switch screens, and I switch screens. I'm just going to glance at the chat before we go over. Then I'm going to bring you over to the homework page. See if I. All right. Okay. Thanks for the feedback. Because like I said, I mean, if you had the 1305, you did cover probability, but there's no sin in being honest and saying, yeah, I mean, there's almost no way you didn't see this if you took 1305, but it's perfectly fine to say, yeah, that you would, oh, you know what? Maybe 1305 is no longer a prerequisite. Okay, might not be a prerequisite. That's why. Because the way they used to do is you had to take 1305 and 1306 before you could even be allowed into 3309. Okay, so it might be a little bit different now. I'm with you. I don't know what all the, okay, then that would make sense. But do students in the business college still have to take 1305 though? You can just take it after this one or whatever? Or, I'm just kind of curious. Okay, that makes sense if you hadn't taken it. Oh, so someone's saying they had taken it, but yeah, I don't know. It might not be a prerequisite anymore like it used to be for the other course when it was a junior course. All right, that's fair enough. So it is kind of new, okay. So some people it's going to be kind of a mixed bag here, I guess. So now somebody's saying they had to take it before this one. Like I said, hey, I'm not here to check prerequisites or anything. You know, I'm not the academic police here. I'm just strictly out of curiosity. So you can be completely honest. You don't have to hide any information from me. I'm not going back and seeing, but I guess that learning, you know, somebody said they didn't learn it in finite math, because probability is, you know, and one of the I know it's covered, you know, so how well or how decently it was covered, obviously that's a different story. But the main things, the finite math, you learn the probability, not necessarily order necessarily. You do all that equations and matrices, and it's okay if you don't remember all that. The financial stuff, the compound simple interest and annuity payments, and then probability is a big part of that course. So so I didn't know if some of you, so it looks like you weren't just totally bored because you knew it, but kind of bored. Not because you're bored because it's math, but because I was just kind of curious to get a feedback saying, hey, everybody already knows this, it's wasting their time. So thank you for your input. I'll go ahead and move on to the homework now. Let's see, I'm just going to pick a couple of these before I move on. And that was a good one. I'm just looking ahead, sometimes. Oh, there's one with the tables there. Those are good. That's what the other one we had was a table also, but that would be very similar. Here's one you got to be careful because it brings up the contingency table. Oh, okay. I could see how reading this out of some sentences could be a bit of a challenge, but if it brings up the table, that's going to help. Ooh, like this one. We have to kind of build the table. Well, that's okay. We'll come back and maybe take a look at that one. I'll go back and look at one of these other ones first. And I'm not saying it's going to be that scary. We just have to think a little harder here. Let's see how many. I don't want to do one that has a million parts to it here, but let's see. It doesn't take that long, really, but I just have to switch screens to be able to write, obviously. Well, actually, I might be able to say it verbally and just tell, you just write down, I'll try to do it verbally here, and then so I can get the answer off these. Well, I'll need the calculator, but if I tell you what I'm doing, and then think you might be okay for these, they're not that bad. Let's just do this one, then I'll jump ahead to that other one. So here's a little contingency table up here. Determining whether or not you're stressed at work, comparing male, female, and stressed or no stressed, whether you're male, female. What is the probability that a randomly selected person's gender is female? So it's just asking female, not bringing the stressed in there. So you go all the way to the right. Hopefully you can see where I'm pointing. You are looking at the homework here, right? I want to make sure I'm on the right screen.
Yes.
Yes.
Okay.
Yeah.
Yeah, that one I did want a verbal answer on. Yeah. Okay. God, I don't want to start talking for 5 minutes. We're not looking at that. 655 females, and then you just divide it by the grand total. I'm not bringing up the calculator screen just to do that, but I'm just going 655 divided by 1390. Oh, I didn't read how many decimals it wanted. I got to go back and look here. Boy, it's picky about that, isn't it? 3 decimals. Like 655 divided by 1390. I get 0.471 is 3 decimals. .471. Let's see how we did. Look at us, 1 for 1 here. Aren't we good? Stressed out feels tense or stressed out at work. That's all. Oh, yeah, you got to be careful here. I don't like the wording on this so much. I almost misread this. See that? Don't confuse that or with the probability or. See, that's I hate when that stuff happens. The key word here is the and. It should just say stressed out at work. It doesn't really need all. That's good enough. That's okay. That or is a little rude there. This is what we're looking for is the and right there. Or just stressed out. Stressed out at work would have been fine. It didn't need that other it didn't need to put that word or in there to make things more confusing. So ignore that or. So now Female and stressed, where do they meet each other? So it's female and yes, right there at that 330. That means you're female and yes to being stressed out. So now I'm going 330 divided by 1390. So once you identify what you're looking for, it's, probably going to have an actual OR question here in a minute. I'm guessing, I don't know. The 3 decimals, I'm getting 237. .237.
Sir, can you repeat that again?
Repeat which part? What?
B.
330, where the female and the yes to stressed meet each other. Can you see my arrow?
Yes, I do.
That means you're female and you're also stressed. Because it's in the yes column. And then I just took that number and divided by 1390. I'm taking all these numbers and dividing them by 1390. Feels tense or stressed out at work, or is a female. Now this one I'm going to write out on another page here because I need to use the formula for that. So I'll copy the table over to a new page because this one would be hard to do verbally because it's going to be 3 numbers. All right, now I'll snip it out of the prop question here too. So snip it out of here so I can have the question on the screen at the same time. Paste it over here. All right, now I got to switch over to this. All right, stop. Let's come back to the new one. Nope, there we go. All right, now I should be looking at the blank page here with the next question here. So we can give these arbitrary letters if you want to. I don't have to write all that. Yeah, I'll just use simple letters here. I'll just use M and F and just Y and N for yes and no and the stressed out. They're hard to see. Let me make them red. So that way I can write this. So you see this actually is, this OR is a probability OR right there. So by using the letters I chose up here, stressed out at work is Y, or female, F. So using the formula, I'm not going to go back to the formula, but you obviously should. Y plus F plus minus Y and F. Now, what I'm going to do right here, since they're all divided by 1390, I'm going to wait till the last step to divide here because I'll do the numerators first. So, how many are yes stressed? I see 710. How many female? 655. How many female and stressed? That's what we just did. 330 right there. They're in the female, they're in the stressed. So I'm gonna do this in my head, and then I'll do the final step in the calculator. And obviously if I'm wrong, let me know. 1365, I think it's gonna be 1035. So it should be the decimal equivalent of 1035 divided by 1390. Sometimes I do that and I'll mess up, but well, we'll know obviously when it comes check mark time, we'll know for sure, won't we? I get to 3 decimal places, 7446, so I get 745. So I don't know what screen I'm on, but I'm gonna stop it. Or I know what screen I'm on. I'm gonna share the answer page now. I'm gonna put in 755. Then I'll copy the next question over to where I was. Check answer. Oh, what happened? 1965. Oh, see, I can't. My memory's so bad. I can't even remember 745. I can't even remember 2 seconds of what it was. Yeah, 745. I just typed in the wrong number. Pretty sure that should do it. Yeah. So I didn't do it wrong. I just typed in the wrong answer. Oh, okay. D is not a count. Okay, so D is just. I thought it'd be another count. Oh, I didn't talk about collectively exhaustive there, so dang it, I have to go back and add that in the notes. I was trying to avoid that. The two events in B are mutually exclusive. That's not true because B said you could be stressed and being a female. That's definitely not it. I got to double check what collectively, so it's not mutually exclusive. I'm going to go with A. No, it must be B then. Yeah, I didn't define collectively exhaustive, so that's on me. But yeah, see, it was B. I knew C was wrong because they weren't mutually exclusive. They weren't two separate. You know, they intersected. As long as you have an and in there, they meet. You know, row and column. They're not. So I guess yeah, it's okay. That makes sense. All right, onward here. Let's see. I was going to take a look at this one. That could be a little tricky. I'm going to have to, how many parts does this one have? Let's see. This is taking longer to get through than I thought. I thought we were going to go through so fast and be done. And let's see. All right. So I got to snip this out and read this carefully. Maybe the conditional probability will go a little quicker, or maybe not. All right, so let me switch screens. So I just cut and paste the instructions over to the same notepad here. Cars needs a warranty-based repair, yes or no? Domestic or foreign? Construct a contingency table. Actually, it's a good practice for us. This will be good. It doesn't make it, and mathematically it won't make a difference, but it's not indicating, like I said, which one we go, row or column. I'm going to go, yeah, this doesn't matter. Like I said, it won't matter numerically, but it just matters as long as I put the right number in the right place, you know. So when we're picking answers here, total, I'm going to use yes and no across the top. And then I'm going to use domestic or foreign along the sides. That's what I was talking about. That's not going to make the answer wrong if you do it the other way, as long as you place the numbers in the right spot. And this will be the total for this. And then you got the grand total there at the bottom. Well, these are going to be probabilities, so the grand total is going to be, if they're already probabilities, they're just going to be 1.1 or whatever, 1.00, just the number 1 is okay. All right, let's see. The probability that the new car needs warranty repair is 0.09. It doesn't specify, which one right there, so that's going to be your grand total. Warranty, yes. The probability the car was manufactured by a domestic company is 0.51 with no other restrictions. So the probability of 0.51 right here. And as I was sort of telling you earlier, all we need is this. We only need is one number on the inside, and we can fill the rest of it out. And they gave us that. So it might look like there's not enough numbers there, but there is. All right, this one's got to give us one of those inside ones. And the probability that the new car needs a warranty repair and was manufactured by a domestic company. That's going to be where domestic meets yes, needing a repair. Domestic, so the way I labeled it, yeah, that's however you label it, it'll be different. But, well, because you could put foreign across the top and the domestic below that, that would have been okay. As long as you put this number where domestic meets. Okay, so it gave us that information, and that's surprisingly enough. I'll do a different color here just to show you. So the red means those are the given numbers. The rest of this is calculated. So that's going to be 0.91. That's going to be, hopefully I don't mess this up, 472. I'm just subtracting 0.351 minus 0.038. Should be that. So this going down should be 0.52 to make that 0.90 going down. And this has to be 0.49. And this one you can get two ways. Either make it add down or make it add across. It's got to be the exact same number, whatever you prefer. So I'll go across. 490 minus 52 should be 38. I think that's it. Yeah, and that would add down to make it 0.91. So there's how you complete the rest of your table. So now I'll bring the questions back over here. I'll just bring each question as we do it. I won't switch screens. I'll just go get it and bring it right here. Oh, crap. I had the entire problem shown, and then I went back to uncheck the show completed problems, and it changed the numbers. All right, let me go back over here and fix this. Dang. I mean, not by a lot, but enough. Well, any changes at all. Dang it, I should have remembered to do that. Because I was just looking ahead to see how many, what kind of questions it had. That was 039 in the new one. Warranty is now 0.08. So you see it's just slightly changing everything like it normally does. 0.03, I got that number. 7.73 is domestic. Yeah, as I can't get my check marks if I don't get the right numbers in. Okay, so I'll do the same thing I just did. Fill out the rest of this. That'll be 0.92, 0.27, and 730 will be 691. 041 and 229. That should all add up and down now. So, all right, now, okay. Now I'll get the question, drag it over here, and we'll take a look at it. Um, what is the probability that a new car selected at random needs a warranty repair? Let me read that. Am I missing something up here? Is it that easy for this one? Well, I think it's just the .08. Something's weird about that.
I think the top, it was from the first problem. Didn't the numbers change?
Oh, the numbers. I'm not talking about the numbers. I'm just talking about the question itself.
Oh, okay.
You're saying, yeah, it's new numbers now or whatever. Yeah. Yeah, I'm not looking at the .09. I'm looking at the .08 right here. I'm just asking. I'm just surprised it's asking a question where it would just give you where it's just the numbers right there. Oh, whatever. That's okay. I thought it would be using these numbers to do something else.
I guess it's thinking the work was really done by making the chart, I guess.
Yeah, that's a good point. That's a very good point.
And if you did the chart right, then you'd get these answers right.
Yeah, that was it. So let me drag part B over. Yes. But I thought, it would be looking for one of the missing numbers. That's what it would have made more sense to me is one of the missing numbers, or even asking what's the probability that it did not need repair, whatever. That would have, that's one where that's only what surprised me. But I do agree with you though about it is all based on doing the chart correctly. But all right, well, I'll go back and show you, but it did not give me an error. That one was right. Let's see what part B is. Oh yeah, here's what I was getting. Yeah, getting the inside numbers here now. Warranty and domestic. Well, they gave us that number already too. This problem's ridiculous. I hope that the last two questions are actually real questions. It's just going to be the .039. I want to answer something that's actually that we went to all that trouble for nothing. Yeah, that was right. Give me something here. Give me finally. Thank you. They put an or in there. So now I feel like we did that for a reason. But actually, we still didn't need the chart to do that, to do this one, because it was the numbers that was already given. So I don't know. I guess maybe I thought for sure they'd want us to build the chart, but that didn't hurt showing how to do it. Because it's using the same numbers. They say, in other words, so this would be so warranty or domestic. So it's probability of W or domestic is the probability of W plus the probability of domestic minus the probability of warranty and domestic. Yeah, those are the three numbers it actually gave us. Warranty was 0.8. It's those three red. It was the first. It's 0.8 plus 7.3 minus 0.39. I'm going to be disappointed if we're not going to use any of those numbers that I found. Let's see if I can get this right without a calculator. I did the other ones. Let's see. It's going to be 81771. I didn't say that with much confidence, did I? I feel good about it now. 771. So I'm not going to switch back, Max. Obviously, I will not lie to you. If it's wrong, it's wrong. I'll tell you. That was right. Oh, we might have something here. It almost seems like, you know, have to complete all that to only answer one out of the 4 questions is weird. I liked part C, though. That was good. But it's just the first 2 didn't seem really, when they practically just typing in the number it gave you. Warranty or foreign. Yeah, now we needed those numbers. Probability, warranty, or foreign equals probability of warranty plus probability of foreign minus probability warranty or warranty. Warranty or foreign. Our warranty we already know is 0.08. Now, what's the probability of it being a foreign vehicle? Right here. 0.27. That's the second number. And then now we've got to find out where does warranty meet foreign. Warranty meets foreign right here. 041. Yeah. Uh, 309. So that's right. Fantastic. I'll go back over that one. So you notice that, so, you know, when your contingency table is already in probability form, you know, you don't divide by anything, but if they're whole numbers, you have to divide by that number at the very bottom, right? But they're already divided. When they're probabilities, they're already divided. So look at that. I want you to see my fantastic, and everything's all completed there, right? So that was good. So, all right, this would be a good time to take a break. Hello out there. Welcome back to the show.
Hello.
Let's knock off part 2 here for today. And then see what kind of other things you'd like to ask about. Go ahead and open up this next homework. So let's see where we are. Should be. Are we looking at the 4.2 conditional probability?
Yes.
Yes. Yes.
Wonderful. That's terrific news. Conditional probability. What in the world is that all about? Now, it has a formula. It's also, you know, some of those ones with the contingency tables, I'm going to show you sort of a way you can do it with or without formula. It'd be, you know, you choose whatever's best. When I say formula, it's not that complicated of a formula. But the non-formula way might be a little tricky, so you can decide what's best for you. Conditional probability means you're trying to find the probability of some event given that you somehow know information about another event. So you're trying to find the probability of A given information occurrence of another event B. Now sometimes that B would not affect A, you know, it's going to be something we call independent events, but a lot of times it can. Just kind of give you a couple of examples before we jump down the formula here. One common example is drawing a card out of a deck. let's say, and I think we're gonna look at that later. Actually, that example. It's that same one. If you take a card out of the deck, and then you're going to draw another card, and you're going to say, what's the probability, you know, that I draw a diamond out of there? Well, the probability, but then probability of diamond, given that I drew whatever the card was before. So if you know what it was before, you know, that's going to affect your probability. You need to know, you know, did a diamond come out the first time? Did a diamond not come out? You know, so it's given information. You know, you don't have to worry about how would you know that information. You don't have to analyze it in that much detail. It just means you know some sort of an event. You know, like here's one, like the let's see, let's say you roll a single die, and we'll say, let's say what's the probability that you roll a 2? We'll just use a basic example. Roll a 2. Well, it would be 1 out of 6 because there's 6 total outcomes. So you'd have a 1 out of 6 chance of rolling a 2. But what if we said, what's the probability, and then defined another event, what's the probability of rolling a 2 given that we know we rolled an even number? In other words, however you know, it doesn't matter, but you know that it's even. If you know that it's even, you no longer have 6 numbers to choose from, correct? You would only have 3, a 2, a 4, and a 6. That seem right? So if you know that, a 2, a 4, and a 6, the probability of rolling a 2 given that condition would be 1 out of 3, not 1 out of 6. So that's essentially the idea of what we're doing here. Let's look at this first formula. That vertical bar is not a mathematical symbol. It's not division. It's not anything like that. It means given that, such that, you know, that's the common phrasing. So the probability of A given B is the probability of both A and B occurring divided by the probability of B. Now, notice if you switch this around, the probability of B given that A occurs, it's the same numerator, but look at the denominator. It's probability of A and B divided by the probability of A. And in fact, on all these type of problems, no matter what lettering you're using, it's always true that the denominator probability is always the probability that's on the right side of the condition symbol every time. So you see that's a B, so it makes that a B. This is an A, makes that of it A. And there we go. And this is what I was talking about. The example I just explained to you about the dice and the 2, 4, and the 6. That's how you would explain. I was actually explaining this same problem here. I forgot I'd already had that problem. Okay, that's good. I actually had this one in the notes already. I didn't know if I did or not. So that's the one I was just explaining, was this one. So you know that one I did without using the formula. Now I'll show it to you with the formula. It was 1 out of 3, kind of doing it logically, but look at the formula. So if A is rolling a 2 and B is even, so the probability of rolling a 2, given that it's even, would be the probability of A. I use that intersection symbol, but remember that's the word, still the word and, means and. It's whenever it's a U, it means or. And A and B means that, okay, so let's think about that. A and B would be the event of being 2 and being an even number. So that's one way to intersect those two, because A will have 2 and B will have 2, 4, and 6. So the 2 is in common. You got a 1 out of 6 divided by the probability of B, which is rolling an even number. So there are 3 even numbers, 6 total, 3 out of 6. So using the formula, you get 1 out of 6 divided by 3 out of 6, which equals 1/3. Which is what I was explaining about if you just eliminated, you know, you reduce the sample space. That's what you're effectively doing, is reducing the sample space. Now let's reverse this. What if you want to say, what's the probability of rolling an even number given that you know it's a 2? Now I use the formula here, but common sense kind of dictates this answer, but here's the formula. The common A out of, same numerator, 1 out of 6. The probability of A rolling a 2 is 1 out of 6. 1 out of 6 divided by 1 out of 6 is 1. but meaning it's 100%. But if you think about it, now think about the wording on that one. Reversed, B given A. The probability of rolling an even number given that you know it's a 2. Well, duh. It has to be an even number if you know it's a 2. So there really isn't much to that. But the formula bared it out that it was a 1 there, you know. So yeah, well, of course it's even if you know it's a 2. So that one kind of cracks me up. All right. Here's what I was sort of explaining earlier, that if you know, for the first one, if you know it's even 2, 4, 6, and the probability of getting a 2 would be 1 out of 3. But the formula bears that out. And we may use these probability trees to do some of these. Watch out. We'll take a look at an example of this one down below. I'm not going to let these trees get very, very rude. You know, I mean, I think 2 branches is enough. I don't think we have to make that big of a production out of it. So let's take a look at something. Now this is okay. This is the first time we've done one with like different balls. Balls and marbles are often common probability experiments you can solve. But this one, look at this one. This one has a box with 4 red and 2 white balls. Oh, I missed typo. I might repost this one just for construct, not construct. Without replacement. Now, this is very important. With and without replacement. That's important for things like this, drawing balls out of a box, drawing a card out of a deck. If you replace that card before you draw the next time, that's totally different than if you draw that card and leaving it out. Now, some experiments that would not, it makes no difference. There's no such concept of replacement. Rolling a single die. Like if you roll a number on a die, you don't suddenly just sandblast that number off and you can't use it again. So you can, you know, it automatically repeats, or flipping a coin. But anything that's an actual physical item like this, you know, a card, you know, or the ball from a box, it does make a difference whether it says, you know, with or without replacement. So the first branch of the tree is pretty straightforward. 4 red, 2 white. R1, white 1 means red on the first draw, white on the first draw. 4 out of 6, 2 out of 6. Now the next ones are conditional probabilities. I think I mentioned that somewhere in the notes here. These are actually all conditional probabilities because it's not replacement. So when you go up this first branch of this tree, these 2 probabilities are based on a red one coming out of the box. And then the bottom 2 will be based on a white one coming out of the box. So these probabilities here are not just red 2, white. They're red 2 coming from red 1, white 2 coming from red 1. They're not just red 2 itself. I'm going to show you the formula for that here in a minute. If you just flat out asked what's the probability of getting red on the second ball, it's not these numbers right here. These are conditional probabilities. Now notice that all these numbers on the second branch are divided by 5. That's because whether we've pulled a red one or a white one out, we've taken a ball away, right? A ball's gone. So you're choosing out of only 5 on the next. That's what I was talking about, the replacement. The replacement would be pretty boring because these would all be 4 over 6 and 2 over 6. 4 over 6, 2 over 6, 4 over 6, 2 over 6. Yeah, if it'd be the same scenario every time, where's the fun in that? But this one's fun because it makes you think a little bit. So let's see how we get these 2 conditional probabilities on this branch coming from red 1. Not too bad when you think about it. That means coming up that first path, a red ball is gone. So we're down to 3 reds and 2 whites. So if we have 3 reds and 2 whites, we're going to have a 3 out of 5 probability of drawing a red one if a second time if a red one was taken the first time. Which means white will be 2 out of 5 because both white balls are still there. So it's 2 out of 5 for the white. So let's go down to the bottom part of this branch. That indicates a white one was drawn the first time. So dynamics here change. So it now becomes all of the reds are still there. So you have 4 reds and 1 white ball. So that means the probability of choosing a red one on the second one, given that you had a white one on the first one, would be 4 out of 5, because it's now reduced down to 5, 4 reds, 1 white, 4 out of 5, and then the white one would be 1 out of 5. That's, takes maybe a little practice there to kind of get used to it. Now we have something called a multiplication rule, which is just based on multiplying. It's taking this conditional formula I showed you earlier and essentially just solving for the numerator by bringing the bottom up. So it says that the probability of A and B can be found as the probability of A given B times the probability of B. Now this can be expanded to, this is the marginal probability using the general multiplication rule. So let's, so if you had more branches and more stuff, you can, with this one we have 2 branches, so we have 2 of these to consider. But if it was something like, I mean, I'm not going to do this, but let's say you had red, white, blue, green balls, and red, white, blue, green, red, white, blue, green, it would just expand the formula out. I'm not going to do that. This is enough right here as far as I'm concerned. So these are all, as I mentioned, these are all conditional probabilities, which I'll list these right here. Red 2 given red 1. So that 3/5 number is red 2 given red 1. It's a conditional. This one, 2/5, is white 2 given red 1. Down here, so 4/5 is red 2 given white 1. And the last one's white 2 given white 1. And there I just listed all 4 of them out right there. So you can see those. So if you look at this later and going, where'd those come from? Go look at here and then go back and look up at the tree. And there you'll find it. So now, here's a question I was asking earlier. What if the question just says, all right, I want to find the probability of drawing a red ball on the second draw. We're not even focusing on, it's considering both possibilities of it being white or red the first time. This one, you kind of have to use the formula for this. You can't really do it intuitively. You kind of have to use the formula. And it's using this bottom formula. So basically, it's anything it's the conditional. It starts out with, you see that's an A right there, then that's an A. So it's probability of red 2 given, it's anywhere that red 2 can come from. Red 2 given red 1, and then red 2 given white 1. So that's what I was talking about, how this formula would expand. Let's say if it was red, white, blue, green, you were doing red 2, you'd have to do red 2, red 1, red 2, white 1, red 2, blue 1, red 2, green 1. So you'd have to do everywhere it can possibly come from. So red 2 comes from red 1, and then you multiply it by the probability of red 1. Now red 2 comes from white 1, so you multiply it by the probability of white 1. Starting to get a little tricky, I know. But this one, you just kind of, the conditional probabilities, you can, like I said, you can figure them out the way I was doing it off the tree, and they kind of make more sense logically because you're only coming from one route. This one's allowing both of them. So you take the 3/5 times red 1, which red 1 was just a 4 out of 6 probability, plus red 2 given white 1 is 4/5 times the probability of white 1, which is 2 over 6. I just reduced the fraction, but that ends up being 20 over 30 if you work the numbers out. 20 over 30 reduces to 2/3. I don't know on an exam whether this will be fraction or decimal, but my math lab probably decimal anyway, so it wouldn't matter whether you did 20 or 30 or 2 over 3. You're going to have to divide. So that means there's a 2 out of 3 chance you can get you'll get a red ball on the second draw. So you just kind of have to follow that formula and, not worry about it intuitively there. We'll see if that comes up in any of the homework problems here in a minute. Now, independent events, sometimes, it's obvious certain events are independent, but you don't always assume that because sometimes they can be independent and you not realize they are. Basically, they're independent if the one outcome doesn't influence another, but mathematically, more specifically, two events are the probability they're independent if the probability of the joint probability of A and B, if it equals the two individual probabilities of A and B multiplied together. Now let me give you an example of events that certainly would be independent. Coin flips would certainly be independent. If you were asked, okay, what's the probability that I flip a tail, given that on the sixth flip, given that you flipped 5 heads in a row before that? The answer would still be 1/2. They do not influence the outcomes of previous. Now I talked about, the law of large numbers where it should even out in the long run, but the coin doesn't know it can't come up whatever heads or tails, so you flip it and it doesn't matter what the previous attempts were. The probability would still be 1/2. So it's independent. Anything, well, drawing a card from a deck only if you replace, and same thing with the marbles. If you replace them, they're independent events. If not, they're for sure dependent. But this formula, let me write out real quick a sample space. I had that in the last section for boy, girl, which is actually the same as 2 coins, tail, like that. So that would be the 4 outcomes for a 4-coin toss. The probability that you get, heads, let's say heads and heads back to back. You can see that there's 4 outcomes on total, and there's one way you can get head then head. So the probability of head 1 and head 2 is 1/4. The probability of head by itself on the first one, head 1, would be 1/2. Probability of head 2 would be 1/2, because it doesn't depend on, so you see the 1/4 equals 1/2 times 1/2. So that's just sort of a way that it proves it's independent. But coin flips are definitely independent. And here's just another formula to try to confuse you here or whatever, but it's not that big of a deal. But this is, and it kind of makes sense if you look at this formula. The probability of A, if the probability of A given B is the same thing as probability of A, that means they're independent, because that means B had no effect on A. And same thing here. Probability of B given A, if that's the same as the probability of B, that means A had no effect on B. It was not dependent upon it. So, all right. So let me erase that, and let's see. I asked a question about the marbles up here. Let's see. R1, R2, independent. Okay, because this helps that we've already calculated the R2. That was one we had to go through this process, right? It wouldn't have been this easy. In other words, I had to do the R2 first. R1 is easy because R1 is 4/6. So the I didn't mention this. The probability to get the ands here, which just means and, the probability of R1 and R2, it's actually using this formula right here. You multiply along the paths. You're using this formula. So the probability of R1 and R2 twice in a row would be 4/6 times 3/5. You would multiply those two numbers there to get the ands. R1 and R2 back to back would be those two multiplied together. So what I'm showing down here is that here's R1, here's R2 that we just figured. Here's R1 and R2, which I'm then showing as the multiplication of the two. So 4/10 does not equal 4/6 times 2/3. So they're not independent. And we were pretty much sure these weren't going to be independent anyway. That just backs it up, because obviously It was dependent because it depended on, what color ball you chose the first time. Anyway, that just proves it numerically. Okay, here's one. Okay, so if you had several events, so like coin flips, so probability of, head 1, head 2, head 3, head 4, but they'd all be independent, and you'd multiply their probabilities together. Okay, no big deal. Let's do another tree problem here. That could be fun. So I didn't change a lot of these notes. I just keep saying that, don't let that confuse you. That upside down horseshoe, that always means and. I was, using notes from another course. Put these in there. And that course was not using and or. It was using this more of the symbols. 2 cards from a standard 52 card deck. It's actually asking a red question again, but not red marbles. This time it's red cards. It's asking what's the probability of getting red back to back. So both cards are red means red 1 and red 2. So it's not asking just red 2, which we could have figured out red 2. I can tell you, without writing it out, I can sort of tell you after we finish this. But so here's the tree. So you got 26 out of 52, 26 out of 52. Going up the first path means we lose a red one. So that means we lost one full card. So there's 51, but you lost a red one. So it's 25 over 51. And now you've got all the black ones. So it's 26 over 51. Now I didn't mention this with the last tree. That's okay. We did everything right. But let me mention with this tree, just so FYI here, the sum of the branches on any branch of a tree must add up to 1. Every branch sum. So these two, you could double check it in case something went wrong. Like, oh, if those didn't add up to 1, we'd know there's a mistake. Like say, suppose I made a mistake here and made this bottom one also 25 over 51. I would add them together and get 50 over 51, and that wouldn't be right. So the branches have to sum up to 1. So, and we go down here, and the bottom one means we lost a black card. So all the red ones are still there. We're still out of 51, 26 out of 51. And then the black ones, we lose a black one, so it drops 25 over 51. So to go red 1 and red 2 in that order, you just multiply along the path. 26 over 52, 25 over 51. We multiply. It's that number right here. Part B is really easy because you don't have to even redo the tree. There's no need in doing the tree because if they're with replacement, it's just going to be, or you could actually say 1/2, but yeah, 26 out, yeah, so it's just going to be 26 out of 52, 20 times 26 out of 52 because all the cards are in there again, so we didn't need a tree to show that one, 1 over 4. So I mentioned the tree is not independent, not necessarily because they're independent. But I'm not going to write this one out, but suppose it would have asked probability of red on the second card like we did earlier with this marble. You would have gone these two numbers, red 1 and then times red 2 given red 1, those two. And then B1, 26 over 52, leading to red 2. So you multiply along the path leading to whatever you're trying to figure out right there. Sometimes that's easier to understand than the formula. So if we're trying to get to R2, we multiply every possible way to get to R2. And then we'd add those numbers up. So here's another one, our 52 card deck. We're defining M as a diamond and N as an even card, not counting face cards. So those of you for you blackjack players there, we're not counting face cards as 10 value cards. When we say even, we literally mean the numbers 2, 4, 6, 8, 10. So from the last section, I won't go about, I'll just mention it. So there's I'll do the bottom. 1 out of 4, 13 out of 52, there's diamond. Total number of even cards. Each suit is going to have 5 even cards. 2, 4, 6, 8, 10. 5 of those, there's 4 suits. So that's where the 20 is coming from. There would be 20 even cards. 4 2s, 4 4s, 4 6s, so forth, so on, 20 out of 52. Now, the probability that it's both even and diamond. even diamonds, there would be 5 of them. 2 of diamonds, 4 of diamonds, 6 of diamonds, 8 of diamonds, 10 of diamonds. 5 even diamonds. So now it wants probability of n given m. So we can just use the formula for this. We don't need to construct a tree. I mean, we could, but we can do this with just the formula. So the probability of n given m would equal the probability of m intersect n, and then what's here on the bottom, remember, is always the probability of what's on this right side. So I'm not using this, I'm using m right there. Actually, we're only drawing 1 card anyway, so that, now I think about it, a tree really wouldn't make much sense. There's no branch, the trees are when we have, you draw or do something twice in a row. So this one, we just want to use the formula. We don't need to really draw a tree. But it's important we realize that because m is to the right of the conditional, that's what's going on the bottom. So it's the m and n, 5 over 52, divided by m, which is 1/4. To put the 5 over 13 on bottom, the question would have had to reverse the m and the n. I'll write that down here in a second. And that reduces to 5 over 13. Now we're asking, are they independent? And, it's 2 ways you can check it, but one way I checked it was because since probability of n given m that we just got is 5 over 13 does equal the probability of n, 5 over 13, that shows it's independent. So let me write out real quick just so you can see this. We got one more page and we'll be done. Well, I'll go to the homework, obviously, but m given, let's say if it would have asked, in other words, what's the probability that it's a diamond given that it's even? Same numerator, 5 out of 52. Divided by the probability of n right here, 5 over 13. That flips over. 1 over 4. You'd have a 1 over 4 chance that it was a diamond if you knew it, if you knew that it was even. All right. Let's jump over here. I think we got the contingency tables coming up. That's always good because that's in the homework, and I'm sure it'll be on my exam review for exam 2. So yeah, here we go. See? Let's do one of these, and then we'll be doing it in the homework also. Well, okay. So we're talking about male, female. Hey, okay, this one's interesting because now it's treating the males as not the females. I like that. So you're either female or not female. That's all right. We can use anything we want. I think I did use F and M down here, colorblind and normal. So they're using, since there's only 2 events, whatever the other one is, it's always prime, but I'm using C and then N for normal. That's fine. I don't think you'll be asked necessarily. Your answers are going to need to be probabilities, but it was just asking to convert this table over to probabilities, which then now that we have them as probabilities, we don't have to divide. But remember, you can do them as numbers, and then you still divide at the end to get the grand total. But all this is, right here in part A, is every number in that table divided by 1,000, that grand total right there. All right, I'm going to show you this question from the formula. Then I'm going to show you, I'm going to sort of explain an intuitive way to do it, which you can sort of say, no, that's too confusing. I don't like that. So that'll be fine. As long as you can get it this straightforward way of the formula, that's fine. What is the probability that a person is a woman given that the person is colorblind? That's very important because that affects the order of how we write the conditional statement. That's important. If excuse me, if it was combined, if it was an and, If it said woman and colorblind or colorblind and woman, that makes no difference. But conditional probabilities, the order matters. F, female, woman, given, colorblind. Formula-wise, it would be probability of F and C given the probability of C. Now, I don't know I guess when I did this problem, I just added this in last night before I posted these notes. So when I've done this problem in the past, I divided right here. But technically, you obviously, I may fix that and repost that. But, since the decimal numbers are here, you can automatically use 0.002 right here. But if you were just looking at this, you wouldn't necessarily be doing that table anyway. You'd probably be working with the whole numbers. So you'd be saying 2 out of 1,000 and then divided by where female meets colorblind. No, wait, that was female meets colorblind. And then divided by colorblind, because it's the part that goes after here. 26 total colorblind. So 26 out of 1,000. So it's 2 over 1,000. Of course, you could use these decimals. Divided by 26 over 1,000. 1,000s cancel. You get 2 out of 26, which is 1 over 13. So here's what I was talking about, without using a formula, how you can do this. But if you don't like this, that's okay. Some do, some don't. This one actually, we won't be dividing by 1,000 doing the method I'm about to tell you right here. Ultimately, we won't even be bringing the 1,000 into play for this. What is the probability that a person is a woman given that the person is colorblind? Okay, if we know that they're colorblind, there's only 26 colorblinds right here that we know. That's in other words, we've reduced our total, and we know it's coming from the colorblind only. Out of those colorblinds, we then look at the male and the female. And out of those colorblinds, there are 2 females. So 2 females divided by 26 total colorblinds, and look at what I have right here. So if you don't like that, you can put your fingers in your ear and go la 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 la. Just make sure your microphone's not on. And that's what it ended up being right here. 2 out of that 26. Maybe we'll try one here in a minute that I don't have listed. I'll make it up, but like I said, without using the formula, we'll just see. And that's okay though. You can always use the formula. The next one says probability that a person is a woman given that the person is colorblind. Wait, I reread the same question. Probability the person is colorblind given that the person is male. Colorblind given male. Which I guess, maybe I should, maybe I should just change that. But I just treated the not, so it's okay. Some of the women out there might want to leave it as not female. That's all right. Hey, as long as you put the right number in the right spot, who cares? But I didn't know if that would make it easier to understand, and I went ahead and changed it to M for male there. So using the formula, we would find the probability that it's colorblind and male, which you see I've already got right there. Colorblind meets male. So that's just this number already divided, 24 over 1,000, divided by the one that's to the right of the males. Probability divided by the male. Which is how many males are there? 480 out of 1,000. So it'd be divided by 0.48. So divide that 1 out of 20, which is 0.05 or something like that. So probability they're colorblind given that you know they're male is 0.05, 5% chance. But you could have done it as also saying, okay, if we know that they're male, I'll go back up here. I like this better. We know that they're male. They're coming out of that group of 480. It's not the grand total. It's just that 480. And then out of those 480, how many are actually male? 24. So it's 24 divided by 480, if you want to do it that way. So I'm just going to write one down here. Probability, and I'm going to do another one by this method. Let's see. And I'm not even going to get the decimal. I'm just going to write the fraction answer. I'm going to do it by using what I was just doing here. And I want to say, what's the probability that they're normal given that we know they're female? Now I'm going to pause for about 15 seconds here. You don't have to orally answer. That way, if you want to think about it, then I'm going to write the answer down. So that gives you a chance to sort of, if you want to think you get it, and then, you know, you can internally, please don't microphone it, but you can internally say, you know, woohoo, if you got it right. If you didn't, that's okay. Obviously, this is not an immediate concern, so this isn't on the first exam, but I get this answer, 518 divided by 520. Because given that they're female, means we know there's 520 females. Out of those females, 518 were normal, means not colorblind. Ta-da! But you could have used the formula and got it right that way too. All right, it's I think it's about homework time here. Look at a problem or so. So we can cut this off, and yeah, that was it for the actual notes, which is fine with me. Let's pick a good problem or two, and remember we can always come back to this later. Does it let me in, or did it expire? Is that it? Okay, let's see. We'll come over here and just kind of we'll look together here now and see what we can come up with. Oh, I see somebody said they couldn't hear anything. I hope that was just when I was on break and I stepped out of the room and I wasn't talking. Yeah, you're not going to hear anything when I'm on break if I'm away from the computer. So hope that was it. Hope somebody's not having audio trouble out there. Because I don't know how to fix that. That's beyond my level of expertise. But yeah, I tend to go sort of, you know, silent whenever, you know, I go on break. So. Of course, if I was really mean, which I'm not, I could after a break I could type in the chat, can y'all hear me now? And if I wasn't really talking, that would just be kind of mean, wouldn't it? But can you hear me? I wouldn't do that. I mean, and I wasn't really talking. All right, so let's take a look at these. So I wouldn't do that to you. Here's something asking about independent. I want to pick something a little more, you know, juicier here. I'll go back. The independent's real easy. If you multiply those two probabilities together, they have to equal the one on the right. I can already see that one's not true. Let's get something a little more interesting. Let's see. Here's another stressed out female thing. Male, female thing, excuse me. All right, here's something different. Maybe we'll try that one. Card problem. I mean, I could just do one of these now, and then I can always come back next week's lecture and start off, you know, with one of these as a review or something, just so we can get to other questions you may have. So I'm going to just do one for now. I'm not opposed to doing another one of these later. Let's see. I'm going to just complete the problem and look and see what we got here. All right. Okay, this is interesting. Because the wording on this is interesting. Sometimes the given part can be written at the beginning of the sentence. And this one using they're using suppose instead of given. Let me go back to the notes and show you what I mean. So you got to be a little careful on this. I have confidence in you. It's just more like sentence structure than anything else. I'll just take a look at part B here and this at the last problem there. So this sentence, this part B could have started out, it could have said, given that the person is colorblind, comma, what is the probability the person is a woman? So you still have to realize that even though the given's the beginning of the sentence, it goes after that vertical dash in the formula. So yeah, you have to realize whatever's given, whether it's written in the first of the sentence or the second part of the sentence, is after after the vertical thing and the conditional probability. So they've actually done that here. They've worded it with so let's take a look at this. Now we should be back on the homework here. So let me just snip all this out and I'll go back to my scratch page again. Go back to my scratch page and then we'll go share this screen now. Where are you, scratch page? There we go. All right, let's see. So it should be back on the scratch page here now. Let me kind of shrink this down a little bit. I don't know what's a good choice labels there for B2B, B2C. You know, if you're trying to use simple letters for this, I'll just use B2B and B2C. Yeah, I'd prefer a single letter designation, but obviously B is no good. I don't want to use B and B prime. That's no good. All right, so here's where we got to get the wording on this correctly. This says, suppose you know that the marketer is a B2B marketer. All right, that's your given. That means automatically, we got this going on. B2B goes second. So it's not the order they present it in the sentence. It's whatever's related to the given or suppose that goes second. What is the probability increase social media? Okay, so that just puts a Y right here. You see that column says increase use of media, yes or no. So it's yes, given B2B. Now I'll write the formula out here. We can do it that other way. Plus probability of Y plus probability of B2B minus probability of Y and B2B. Probability, everything's over 2,000. So I'll kind of just sort of do one big thing like that. Yeah, if you're using the formula, everything's over 2,000. If you're doing it my other way, that just means you're changing the denominator already. But this is oh crap, wrong formula. Pretend like you didn't see that. That was for the or. I'm still stuck on that. Excuse me. All right, easily fixed. Never mind. It's this. Probability of Y and B2B over B2B. All right. Oh, thank goodness I start writing any numbers in there. And these are both going to be over 2,000. That's your grand total. Y and B2B, I'll just circle it. I believe that's right there. That's where Y meets B2B. 545. How about the total of B2B? 1,000? Oh, beautiful. I don't even need a calculator for this. But yeah, I'm not saying you should. I can just tell it's going to be 0.545. I won't switch screens. I'm just going to go over there and put the answer and then fetch the next problem. Wait, I already forgot what it was. 525, 545. Let's see. 545. So the conditional probability getting it in the correct order is key. Okay, let me snip this one. I got a little check mark there. So let's bring this one in for you so you can see part B. This is actually a good way to start doing these problems. Just bring them over. I guess one way you know that I'm getting them right, I mean, I think, is that I wouldn't even be able to see the next part if I didn't get that part right. So I guess that's another way to prove it, isn't it? Suppose you know it's a B2C. Plans to increase social media. So I think that's just going to be probability of Y given B2C. So it's going to be probability of Y and B2C. Probability of Y, B2C. I mean, no, just B2C. And let's see. Okay, everything's going to be over 2,000 again. Let's go back up here and see where Y meets B2C. I better erase these. Y meets B2C. Right here. 730. And B2C is 1,000. I don't really like that in one sense because, I mean, this is correct, but I just, from a student standpoint, I just want you to make sure you realize that's not the same 1,000. You see the difference? It's just a coincidence that they're both 1,000. Yeah, I'd really like those to be different numbers if I was creating a problem, especially like on a test or something, you know, I'd want those to be different just for that reason. But it's not the same 1,000, it's just coincidence. I think it's going to be 0.730. Nice work, it told me. Okay, now I'm just going to go to the homework. The next one's not a calculation, it's one of these weird concept questions. Sometimes these things even bug me, but the problem is, you know, I can only eliminate entire problems in the homework, which I did eliminate some of them from the first two sections. I can't eliminate one particular question. Oh, it's just asking independent. That's okay. Which we can check for independence different ways here. So what's the best way we can, let me think I can do. It's asking social media and business focus. Are they independent? We can test it numerically, but I think it's pretty obvious that they aren't dependent. They aren't independent. Well, let's see why, because they have different calculations. The conditional probabilities were both different answers. Are they independent? I think it's going to be one of the no's. Let's see which one it is here. Same as the probability of a B2. I'm trying to see if I can get away without doing the formula for this. Let's try A. No, I think C. Okay. Yeah, they're not the same probabilities, so that makes them not independent. So, All right, so we're going to stop there.